we know that the AMOC is a potential tipping element in the climate system, that it could shut down. We see from paleo data evidences that it might have happened before. And we are not really much closer to knowing when exactly this will happen in terms of timing, in terms of how much degree of global warming would be okay before the AMOC could collapse than we were like 20, 30 years ago, even though we know much more.
Today's conversation is with climate physicist Levke Caesar. Levke works at the Potsdam Institute for Climate Impact Research in Potsdam, Germany. Her current work primarily focuses on the Atlantic Meridional Overturning circulation, aka the AMOC, and its pivotal role in our climate system. Levke's research has produced seminal work on the past evolution of this important ocean current. In October of 2023, she also assumed the role of scientific lead for the newly launched Planetary Boundary Science Initiative at the Potsdam Institute. This conversation was a deep dive on all things AMOC, what we know, what we don't know, and what speculations are for the future of this critical component of our planetary systems. Please welcome Levke Caesar. Levke, great to see you.
Yeah, great to talk to you, Nate. Thanks for inviting me.
You are welcome. So usually when I host guests, I have their location on my globe. But since we're going to be talking about the AMOC, the Atlantic Meridional Overturning circulation of the Atlantic Ocean, I highlighted the Atlantic Ocean as the theme location of the podcast. So you are a world-renowned expert on ocean issues, especially the AMOC, and that's going to be the topic of our deep dive today. But let me first ask you this. How old were you, and what were you thinking when you first decided, I want to be a scientist studying how Earth's natural systems work?
Well, that's a very interesting question, because I have to admit I'm actually coming from the space science side. So when I was young, and I think even at the age of like 8, 9, I was really interested in the formation of black holes, the life cycle of stars. Then I had a period when I wanted to become an astronaut. And that basically sparked me to study physics. And it was then later during my studies that I kind of realized I want to do something that's closer to home and that feels a little bit more relevant. So I still really believe that astrophysics is really cool. And I don't know, physicists might call it sexy in terms of the data, the mechanisms. But I guess I was in about like 22 when I really did my bachelor's in physics, that I realized physics can also be applied to our planet, to the Earth system, and can explain so many interesting and relevant phenomena, whether the ocean circulations, that, basically then when I decided to shift my focus.
Excellent. I shifted my focus when I was on Wall Street and realized that the externalities were not included in our prices, and we were in for a phase shift during my lifetime of the ecology and natural systems on Earth. So, as you're well aware, global heating is in the news. Lots of people are worried and aware of climate change. Oceans are a very integral part of the climate system, but they don't get as much coverage in the news. There are multiple ocean risks that we face: ocean acidification, decline in oxygen content, sea level rise, overfishing, lots of different aspects. But what we're going to talk about today is the ocean currents and how they change and how they may be changing in the near and distant future. So can you start us off by describing what the AMOC is and how critical it is to the function of climate as we know it today?
Yes, sure. So the AMOC, which is short for Atlantic Meridional Overturning Circulation, and I like that name, even though I guess for a lot of people it's kind of difficult to say at first, but it's actually a good description of what the system is. So the AMOC is a system of ocean currents covering the Atlantic, therefore Atlantic. Meridional, because that's the geological term basically for saying something is moving in the north-south direction. And while the AMOC is basically, when depending on where you look, moving in any direction, the main transport is on the north-south line. So the AMOC is transporting a lot of warm saline water at or just below the surface of the ocean northward in the Atlantic. It's really coming even from the Southern Ocean, so it's really transporting the whole length of the Atlantic, these water masses, and then as basically it's going over the equator through the tropics and then entering the colder subpolar North Atlantic region. And basically with that, it's coming into regions of colder air masses above the surface of the ocean. And a lot of this heat is then being transported or basically released to the atmosphere. The water, the surface water, is cooling down, and cold water is denser compared to warmer water. And this is then basically leading to a sinking of the water masses, which we call convection in physical terms, basically. And these water masses then that are sinking down in the subpolar North Atlantic, and the locations are the Erminger Sea, the Nordic Seas, the Labrador Sea. But I guess if you're not an oceanographer, then probably you wouldn't know what these ocean regions are called. So it's basically around the Greenland ice sheet, so to the south of it, to the east of it, and there you have those places of this deep water formation. So the sinking of surface water masses that are being cooled down by the atmosphere, getting denser, getting heavier, and then are going to deeper ocean layers. And when I say deeper, I mean a depth of 2 to 3 kilometers. And then these water masses together form the southward return flow of the AMOC, now transporting colder water southward at depth towards, basically back towards the equator region. And it's mainly this exchange of warm surface water going towards the subpolar region and colder, deeper water going back that leads to a lot of energy transport by the AMOC.
Okay, let me pause you there for a little bit of history, and I'm going to pretend that I don't know much about this, which I don't really have to pretend much. We've had the AMOC current forever, or since there were 7 continents, right? I mean, we've been aware of this and able to look back in time, and this current that you described has been there for a long time, right?
It has been there for a long time. Forever is probably difficult to say.
Yeah.
But yeah.
And is this a new? I know there's a new paper out by your colleagues, I believe, and yourself on the risks that the AMOC poses in the near future. But is awareness of this current, is this a relatively new thing, or has scientists known about this for a long time?
Actually, no. There are. Within the scientific community, this kind of starts with Henry Stommel, who's a famous oceanographer, who already in the 60s basically assessed that this overturning circulation, which first of all is special to the Atlantic, so we do not have this kind of overturning circulation in the Pacific, that it exists, that it's very special in the sense that normally when we look at either ocean currents or atmospheric currents, they would always transport heat from the tropics to the polar regions, because basically the sun is heating the earth in the sense we have most of the radiation going towards the tropics and then less towards the polar regions. And as is usually the case, basically the systems thrive towards distributing the heat more homogeneously. So basically when you have a lot of heating at one place and no heating at the others, you have a movement of either water or air masses from the heated region to the colder regions. But the AMOC is special because it can actually transport heat above the equator. It's transporting heat from the southern to the northern hemisphere. And that makes it really special. And that the system is there, basically, and why it can be there, which is like a delicate balance, basically, of fresh water, saline water, heating and cooling in the Atlantic. That is something that has been known, as I said, for several decades now. And also an understanding of the mechanism that it doesn't have to be there. So that in principle, it's possible that there is no AMOC, or theoretically, we could even say the AMOC could be flowing the other way around. So as I said, we have a northward surface flow and a southward deep flow. We could also have a circulation in the Atlantic where we have a southward surface flow, deep water formation basically in the Southern Ocean, and then a northward deep water return flow, but that's not the case. The way basically our Earth system is set right now, through the fact that we have a heating in the tropics, we have then evaporation of water masses, of the warm water masses in the tropics, and more precipitation, rainfall in the North Atlantic. This balance is basically played out at the moment that we have the AMOC as it is flowing today with the northward surface flow.
Okay, so I'm going to jump around here, but give us the punchline first, and then we'll backfill from there. What is happening to the AMOC now, and what are the risks or the scenarios you see in coming decades or centuries or millennium based on what's already built in?
Yeah, so what we see now is basically a slowdown of this circulation system, very simply said. And while scientifically it's always a little bit difficult to give exact numbers, everything hints towards a slowdown of about 15% over the last few decades. And again, it's more difficult to say why something is happening compared to then just observing it and saying it is happening. But we do understand under which circumstances, what are the mechanisms that could drive such a slowdown. And this is mainly related to a freshwater influx into the subpolar North Atlantic. So I already kind of said that what is driving this ocean circulation is really a formation of deeper water masses, a sinking of water masses in the subpolar North Atlantic around Greenland. And then basically when you have water sinking at some place, you have to have an inflow at the surface that is kind of filling this gap just due to volume conservation. And then this deep water has to go somewhere. And basically with how the Earth is set, the rotation of the Earth, the way it is basically that we have a southward deep water flow and then this surface northward flow. But if we now put a lot of fresh water into the subpolar North Atlantic, what is happening is that the surface water there get lighter, less dense. This is because the density of ocean water depends on two things: the temperature, which I already mentioned, colder water being denser than light water, but also the salinity. And here, I guess it also makes a lot of sense. If I put more salt, more matter into something, I make it heavier and denser. Now, if we put a lot of very fresh water, so no salinity basically, into the subpolar North Atlantic, then we lighten the surface water and we slow down this deep water formation, the sinking of water masses. Now, that's in principle, that is understood, not just in principle, it is understood. The thing is that in real life, it's not happening in the way that we have at every minute, every place in the subpolar North Atlantic deep water formation. So it's not like we sometimes call the overturning circulation a conveyor belt. And I think there you mentioned something that is continuously going, flowing. But actually the deep water formation is happening from time to time, mainly in the winter time, because that's when the atmosphere is specifically cold. It's also then cooling the surface water the most. And then it's also happening at specific locations because it's really a delicate balance of what exactly is the local surface temperature, atmospheric temperature above that, what's the local salinity value. And that's also why it's difficult for us to say when are we really stopping this process, because we do know that we're now putting more fresh water in the subpolar North Atlantic. The Greenland ice sheet is melting. Under climate change, we see increased precipitation over this region, so also more fresh water. But whether or not and how much this is influencing the overturning circulation really depends on where exactly is what happening.
So which is more, has a higher forcing component, salinity or temperature? Like a small change in salinity or a small change in temperature, which causes the water to not descend or to descend faster?
That's a very good question, and it depends. So because the relationship basically between temperature, salinity and density is not linear. So basically how much, when I change the temperature a little bit, it matters whether I change it from 20 to 21 degrees or whether I change it from 5 to 4 degrees. the differences or the effects on density are different. And the same is with salinity. So we can't just talk about the change. We would have to also talk about the background state and then look at the change to say what is more important. And then also when we look at it right now in terms of the more dominant driver is actually the temperature. But in terms of what we human change and how we change it, it's actually the system is more sensitive to salinity changes right now.
So here's a dumb question, but it's my podcast, so I can ask dumb questions. When water evaporates from the ocean is a salt water, but when it evaporates, the salt doesn't evaporate. The salt stays in the ocean. So the clouds just get non-saline water droplets. And the part two of the question is, as we head into a world with a higher standard deviation of precipitation, floods and droughts, etc., does this changing precipitation pattern over the oceans and supposedly indirectly over the land, which would run off into the ocean, does that higher standard deviation indirectly affect the salinity of the meltwater in the oceans and change this AMOC?
So first of all, your first comment, I'm just going to comment that was right. So basically rain is fresh water and the salt just stays in the ocean when it evaporates, which is why when we have more precipitation over an ocean region, we are freshening the water there. We are decreasing the salinity. And yes, I mean, the thing is, unless with global warming, where we can basically say it might depend on the region, but in general, we see global warming globally, so there's warming close to everywhere. When we talk about the changes in precipitation, there it's way more difficult. So we have a tendency of saying, okay, the regions that now receive precipitation are likely going to receive more, and the drier regions are going to be drier in the future. But that's like more a general thing. It doesn't have to be true for every place. But we can see in our climate simulations that, there is a tendency towards more precipitation over the regions where the deep water formation for the AMOC is happening. And that in itself is basically bad for the AMOC because it can slow it down. But that alone wouldn't be the problem. I think a bigger problem is actually the melting of the ice sheets because due to the reason what you said, also snow basically, I mean, that's frozen precipitation. So that is also pure fresh water. And all this melting runoff coming from the Greenland ice sheet and entering the subpolar North Atlantic, that's actually potentially very harmful for the AMOC. But there are also other effects, just basically the surface warming that we see globally in the oceans could also hinder or slow down the AMOC because it's also making the surface water lighter, enhancing what we call the stratification of the ocean, really meaning that there's not a lot of vertical mixing and therefore also hindering the deep water formation. So there are really multiple effects overlaying this. And I could actually get on and go on and on because it gets even more complicated. I listened to a few of your podcasts, and you also talked already about the aerosol forcing, basically, and its importance for climate change. And that actually also plays a role for the AMOC because a lot of the aerosols right now, where they're basically are located in the atmosphere, it's cooling regions that could also be critical for the AMOC and help in that sense, kind of, and basically be good for the AMOC in terms of it's cooling the regions where the deep water formation is taking place, and that might help the driver of the AMOC, but that also really depends on where exactly. And this is something that is different from climate model to climate model, which is why it's so difficult for us to really say what is going to happen to the AMOC.
We're going to get into the implications of this, which are potentially quite horrific in the coming century. But as a scientist, and I can tell from your voice, do you ever feel a sense of wonder that teams of humans with technology and computers and observations were able to figure out the things that you're describing today? I mean, it's pretty cool, right? That we can understand the dynamics of the ocean currents and all that. Do you ever feel like, wow, this is amazing?
when I take the time and take a step back, I guess, from what I'm doing, because I mean, in my day-to-day work, I'm more concentrated on what we do not know and what we haven't figured out yet. And from that point of view, it's also a little bit frustrating because we know that the AMOC is a potential tipping element in the climate system, that it could shut down. We see from paleo data evidences that it might have happened before. And we are not really much closer to knowing when exactly this will happen in terms of timing, in terms of how much degree of global warming would be okay before the AMOC could collapse than we were like 20, 30 years ago. Even though we know much more, but basically in discovering more, we also discovered that there are more uncertainties and more things we do not understand. And that all in all led to the thing that we are still pretty uncertain.
Let me give you 3 scenarios, and you can speculate, knowing, like you just said, we don't know, but you're very knowledgeable on this topic. The first scenario is that the AMOC slows around 15% and stays there, kind of like it's doing now. The second scenario is that it continues to slow, another 50% or something like that. And the third scenario is that the AMOC actually stops in the coming 100 years or 200 years or something like that. Under those 3 scenarios, what would be some of the effects that the world could experience, or Europe and the North Atlantic coast in the USA and Canada? Can you just paint a picture of what the future might look like under these 3 scenarios?
Sure. Maybe just as a feedback question, what kind of climate change scenario otherwise are we looking at? So basically, because that again is very important.
Right.
Are we looking at a global warming world, or are we saying, okay, we keep this level of global warming plus an AMOC slowdown collapse?
Right. This podcast, we talk about neuroscience and debt and biodiversity and climate and economics. Every one of those is unbelievably complex, and this is what we're trying to do. So what you're saying is that let's keep everything constant with climate the way it is right now today. And if we were able to do that, which of course we're not, this is just a thought experiment, then the AMOC would exhibit, under those 3 scenarios I said, it would have certain effects. Or you could look at it as what is at 2 degrees above pre-industrial Celsius, what would do the AMOC? So they're moving in tandem. Let's just say that 2 to 2.5 degrees Celsius in the 3 scenarios I told you.
Yeah. So basically, if the AMOC stays as it is right now, so basically it slowed down by about 15%, then we would probably, see what we link to the AMOC at the moment, which is, I already talked about this global warming signal. You see global warming or warming everywhere around the globe. But actually, when you look at the long-term temperature trends, you can see that the mid-center of the North Atlantic cooled over the last century. Of course, this is not true for every single year. Right now we are having extreme warm sea surface temperatures in the North Atlantic, but the long-term trend for that region actually has a slight cooling signal, which is unique seen globally. And that is something that we link to the decrease in AMOC strength and the decrease of heat being transported. So the AMOC normally transports heat into that region. As the AMOC slows down, less heat is being transported into that region, which is why we can see a global or a cooling signal, a local cooling signal in that region, despite global warming. This is now making it more complicated, because when we change regional the rate of region, or the local rate of warming, basically, if that is different from one place to another, then this has an effect on the atmosphere in terms of when we look at the changes in sea surface temperatures patterns. So that's what the AMOC is doing. It's kind of heating some of the ocean surfaces and cooling others by transporting heat. And this then is being translated to the atmosphere by either warming or cooling the air there. And this then leads, for example, when we have strong AMOC, we have a heating, the local air above that region rises. We have a low pressure system above that surface region, a higher pressure system in the air or higher up in the air. And what I'm trying to say, I'm probably doing a very complicated job in doing is that we have an effect on weather systems. And what has been shown for the AMOC is basically that a slower AMOC can actually lead to heat extremes over Europe in the summertime by influencing the state and location of the jet stream and the weather systems that are moving with that.
So you're saying that the ocean current dynamics of the AMOC would create a cool blob in the North Atlantic, and because of the jet stream and the pressures, that actually could cause a heat wave in continental Europe.
Yes, exactly, because it's determining how the jet stream is located, and that then determines whether the air that is coming towards Europe is either coming from polar regions or whether it's coming from the African continent. And in that case, this would actually favor an air pressure distribution where we have more air coming from the south towards Europe, so hotter air, and therefore can lead to heat extremes.
Okay, so carry on with my speculative question. What would be some of the effects if under these three scenarios, and you can tell me what climate scenario you'd like to choose. I just want to isolate as much as possible. Of course, we're part of a complex adaptive system, so we can't just talk about the AMOC without the other things. But I don't think many people understand the risk associated with just this one ocean issue. So maybe you could explain under a not too bad and horrible a scenario what some of the impacts would be.
Yes, I think maybe I'm talking mainly about the impacts, and with most of them, I think the risk is just going to be higher under a stronger AMOC slowdown scenario. Maybe it's a little bit different for a complete collapse of the AMOC. So what we know about the AMOC is important for, I said it's important for the heat transport. It's also important actually for getting heat from the atmosphere, extracting that and getting it into the deeper ocean. So in a way, it's also important for cooling the atmosphere. We know right now that, and I guess maybe some of you have heard that, the ocean is taking up about 90% of the excess heat caused by global warming.
And how does that happen?
Yeah, basically it's kind of simple laws of thermodynamics and physics that, and I guess you know that. I mean, if you have two systems of different temperature, then you will have a transport of heat from the hotter to the colder system, right? That's basically why we get cold when we go outside in the wintertime. And I think it might be also then important to know that this effect is stronger with water. Maybe you know when you are out in 25 degrees air, it's a warm summertime. If you stay in water that's 25 degrees Celsius for a longer time, you will actually get chilly because the heat capacity of water is 4 times larger than that of air. Basically, it can take up heat easier, but it's also conducting the heat faster away from you. And what's happening really is we heat the atmosphere, and the ocean below that is colder. They are not in equilibrium, and normally systems will always tend towards going into an equilibrium. And because of that, we have a heat flux from the atmosphere to the ocean. Now, the thing is, the ocean is vast. So the mass of the ocean is, even though, of course, it's in terms of depth, it's up to 11 kilometers. So that's not as deep as the atmosphere is going in height. But because the air gets thinner as we go up into the air, the mass of the ocean is actually more than 100 times larger than that of the air in the atmosphere. So the ocean really has way more capacity for taking up additional heat.
So the good news is that our planet has these deep and cold oceans that have buffered the effects of heat from our greenhouse gas trapping activities. The bad news is they've done this largely invisibly without being recognized, and we've taken this buffer for granted. And what an amazing thing that these oceans are so potent, but they've kind of blinded and caused a delay in our ecological impacts, yes?
Yes, that exactly. And it's basically a problem that is emerging right now because you probably know the problems that we see with coral reefs and the bleaching effect. I mean, and that is also due to ocean acidification, but it's mainly due to marine heat waves. And this is something we're seeing now more and more as we're heating up the ocean. And also, it might lead to us taking for granted that the ocean can take up this much heat and, by the way, also carbon. But that is not necessarily the case. I mean, as I said, systems tend toward equilibrium. So if we put more heat, carbon into the atmosphere, the ocean will take up more. But the pace of how fast the ocean can do that depends on how strong the ocean is stratified and how much deep water formation also we have. So basically, the deep water formation kind of acts as a link between the upper ocean and the deep ocean. And if we don't have that anymore, then the upper ocean takes up heat and carbon but is fairly full soon, basically, because that's a thin layer, and it really only trickles very slowly to the deep ocean, and therefore there will be like a delay time. When we have the deep ocean connected to the upper ocean via deep water formation, then we can take up, or the ocean can take up the heat and carbon much faster, and that's important, but that might actually be hindered in the future by this, by the effect itself, by the increased stratification because of warming the ocean. And
I have so many questions, Levke. We're talking about the AMOC in the Atlantic Ocean, but presumably there are currents in all the other oceans as well. We're just talking about the Atlantic one, right?
Yes.
Yeah. And in the past, I've had on a friend of mine, Peter Ward, who's a paleobiologist who's written books. One book called Under a Green Sky, which was about a historical period called a Canfield Ocean, where they became stratified and produced hydrogen sulfide gas, and there was no exchange between the different layers. What are the possibilities of that happening, and what are your thoughts on that?
Well, I mean, in principle, it's never completely going to happen. Right? I mean, even if you have like a very stratified ocean, if you keep warming the atmosphere and with that the upper ocean, there will always be a little bit of mixing and diffusion basically, and the heat is going to travel downwards. But normally, and this is why the AMOC is so important, as I said, that's a place where we have a lot of mixing from the surface ocean with the deeper ocean. And it's basically the difference in, I put a drop of color, let's say, into a water glass or a water bottle. If I wait a very long time, it's going to mix perfectly, but I would have to wait a very long time. If I take the bottle and shake it, I can do it within a second. And the effect is not as big with the AMOC because it is a local effect, but it's still a deep region or a large region in the North Atlantic where we have a mixing between upper and lower or deeper ocean. And that's why it's so important. And the same is kind of happening, as I said, with carbon. So also the carbon uptake of the ocean, it's the same principle. We have an equilibrium between the carbon pressure in the atmosphere and the one in the ocean. We put right now more in the atmosphere. The ocean is taking it up. And the speed depends on the rate of mixing in the ocean.
Okay, so the oceans have taken up approximately 90% of the additional heat in the atmosphere and approximately 50% of the carbon, something like that?
Yeah, I think it's a little bit more. I think it's more, I'm not completely sure about the number, but I think it's more like 2/3 of the carbon.
Okay, so can this continue indefinitely at this pace? I assume the answer is no. And what is the mechanism that reduces the ability of oceans to absorb heat and carbon? And what happens if they can't absorb anymore, or what happens if they can't absorb as much?
Yeah, so basically the mechanisms are slightly different. As I said, it really is related to an equilibrium between atmosphere and surface, and then the mixing basically between surface ocean and deeper ocean. With carbon, we also have the problem that it's a gas, and gases are easier soluble in, or you can dissolve them easier in colder water. So as we are warming the ocean, we are actually kind of reducing the capability of the ocean to take up carbon. I mean, as long as we keep pushing more carbon into the atmosphere, the ocean is going to take up more carbon because we increase that pressure. But if that process is slowing down, then we see, of course, also a faster rise in atmospheric carbon concentration because we have to make the pressure even higher from the atmosphere on the ocean for the ocean to keep taking up. And then the problem is, of course, also that this equilibrium is going to change in the future. Let's imagine we stop with our CO2 emissions and we actually manage to stabilize the atmospheric CO2 concentrations and even reduce them. Then at some point, basically the ocean is going to outgas that additional carbon right now and giving it back to the atmosphere. And the same is with the heat. If we start cooling the atmosphere by going into the right direction, basically, because it's what we want, then the ocean, who's now acting as a buffer, might give that back on long time scales. So it's really also, has to change how we are treating our solutions and our future pathways by having to consider what we are now changing in the ocean system.
So we're going to get our carbon security deposit kicked back to us at the end. So the buffer turns into a boomerang. Once our emissions slow or stabilize, hopefully soon, maybe in 100 years or something like that, the oceans are going to then give some of that back at some point.
Yes, exactly. And we have to take that into account.
Are we taking that into account?
That's a very good question. I think in general, of course, we are aware of that. But most climate scenarios that we calculate, often they stop in 2100.
As if our world stops in 2100.
Exactly, and that's not really an oceanic timescale. Let's put it like that. So I guess often it's not taken enough into account.
So in the Earth system timelines, this is something that's important to look at.
Yes.
Yeah. Okay, so getting back to the three scenarios, let's just say that we don't do anything to abate our emissions and economic growth is somehow able to continue, and AMOC continues to slow. What are some of the impacts on Europe and the world under those scenarios?
Just as a disclaimer, basically, it's in general kind of complicated to really single out what is an AMOC effect and what is an effect basically of a changing Earth system when the AMOC is also changing.
Let's assume that they change at the same rate, the rate they're changing now.
Yeah. So basically, this knowledge is coming mainly from either paleo data or climate models. So, and when we basically look at a climate model, then what we see is that when we slow down the AMOC, we have an increase in storm activity and winter storms over Europe in the wintertime, which is mainly related basically to changes in the sea surface temperatures pattern in the North Atlantic, which is driving the winds, and that's basically what we can see. We also expect changes in precipitation, mainly over summer, and that really depends on where in Europe you look, but in general it seems to get a little bit drier with an AMOC slowdown. The explanation is fairly easy in the way that if we put less heat into the North Atlantic, we have less evaporation, and due to the wind system, normally this evaporation is being transported towards Europe. When we look at the US coast, we actually see an increase in sea level rise. And the explanation is actually quite beautiful. I mean, it's not a good thing, but the explanation is beautiful in a way, because I don't know whether many people know that, but when we would look at the ocean surface, it's actually not flat. So basically, when you look from space at the ocean surfaces, you really have hills and bumps and so on. And that is basically because water masses are moved, and we have, due to the rotation of our Earth, we have a constant force. I mean, physically saying we say it's Coriolis effect, not force, because it's not in a physical definition of force, but basically we have something that is moving the water masses. If something is moving more northward on the Northern Hemisphere, it's being deflected to the right. And now when we look at the surface currents of the AMOC, on the Northern Hemisphere, they are moving northward, so water masses are being deflected to the right, towards the midst of the North Atlantic, which is when you would look at the North Atlantic, you actually have a water hill in the middle of it, and lower water levels, or basically towards the coast of the US. And that is really linked to the strength of the surface current of the AMOC. And if that strength is slowing down, if that current is slowing down, then basically this water hill in the middle of the Atlantic is getting lower, and the sea level at the US East Coast is getting up. And again, it's kind of really complicated to say, or difficult to say, how much exactly that would be. So from climate simulations, it seems like a complete shutdown of the AMOC could lead to an additional approximately 1 meter of sea level rise at the US East Coast. But there it also really depends on the city because of complicated dynamics. But that's, a link that we know of.
And what about the temperatures in Europe if there's a large slowing or shutdown?
Well, if there's a shutdown, it could be locally up to 10 degrees or more. And that depends on, do I look at the annual mean temperature changes?
Hotter or colder?
Colder. If the AMOC shuts down, then because of this missing heat transport by the AMOC towards the Northern Hemisphere and Europe, it gets colder.
So like the movie The Day After Tomorrow, just not as exaggerated.
Not as exaggerated and not as fast, of course. I mean, in The Day After Tomorrow, everything happens within weeks, and that's something of course, it's also important to stress. We know that the AMOC has a tipping point, which means that if we push it too much towards slowing down, there are feedbacks within the system that basically would continue the slowdown process and would lead to an even slower AMOC. But this is not happening within days or weeks, but decades.
Could you just briefly mention one or two of those such feedbacks?
Yes, one is actually, and this is a nice thing, I guess, that we are talking about the same principles. And again, the AMOC itself is, as I said, it's transporting warm and saline waters, surface waters northward. And I said, ocean density is determined by temperature and salinity. So basically, the AMOC, by transporting salt towards the region where the deep water formation of the AMOC is occurring, is actually kind of enforcing its own driver. It is making the water denser where it needs it to be dense to keep going. But if the AMOC slows down, then we have less salt there, and it's a different effect from adding fresh water to the system, but the result is the same: less salt in the subpolar North Atlantic where the AMOC deep water formation occurs.
You are so smart and articulate. And I have to also point out that you are doing this not in your native language. So it's so impressive and important and interesting. So thank you.
Thanks for pointing that out. Sometimes I feel a little bit stupid when I say something in English and the words tumble out of my mouth.
I could never do a scientific climate discussion in English, let alone German, the way that you're doing now. So let me ask you another dumb question. If AMOC slows or stops, it could be up to 10 degrees Celsius cooler in Europe. But this is while at the same time global warming is occurring. So does that mean elsewhere in the world there's somewhere that has a corresponding heat bump to make the whole thing a little bit net hotter, or how does that work?
Yes. Yes. So basically, again, AMOC transporting heat from the southern to the northern hemisphere. If the AMOC stops, we have more heat access in the southern hemisphere. And that is also what we see in any kind of simulation where we simulate an AMOC shutdown, is more heating in the southern hemisphere. Exactly where is difficult to say. It's probably, of course, in the North or in the South Atlantic, so in that region, but it kind of seems to spread globally.
So this would not be good news for Brazil and Argentina, who are already experiencing quite hot temperatures from climate.
Exactly. And I would even go so far to say it's also not good news for us, even though we might have a cooling through an AMOC slowdown or shutdown. And we now said, okay, it could be 10 degrees. It really depends on the simulation, but then we would have to add that a shutdown is probably going to occur. Maybe it occurs under 5 degrees of warming. So you could say, okay, great, we have 5 degrees of warming, 10 degrees of cooling, so maybe a little bit of cooling. But this really, it's very local effects, so we don't know exactly where yet. And that is, of course, a very complicated thing, because it also means on how do we prepare for our future. It will be very different under an AMOC shutdown than it is under a general global warming scenario with just an AMOC slowdown.
There are decreasing benefits in an economy to more complexity. There are also decreasing benefits to conversations with average people due to more and more complexity. And this is an incredibly complex topic, but a simplistic understanding: is there a risk for trying to get people in Europe aware and engaged and voting and doing things to mitigate more global warming, that if they hear that the AMOC is going to slow and that Europe is going to be a lot colder, doesn't that emotionally kind of defer the urgency of climate change at the margin to some people? Have you come across that?
I haven't. And I think that's a very interesting thing that I haven't, because I think it shows that people understand enough about the complexity, and that basically nobody could guarantee them that they're better off with an AMOC collapse. Instead, that we tell them it's really something also depends on where in Europe you live. So it's not going to be like a cooling everywhere in Europe, but it will be really centered about the North Atlantic. It's going to change precipitation patterns. And I think looking basically at the last years with flooding events and droughts and so on, people know that all these changes in dynamics, apart from a simple change in temperature, can give so much additional risks, or bring so much additional risks, that I think a lot of people know, no, this is not something you want to risk, even though there might be a very, very small percentage that's actually going to benefit very few of us.
So obviously you can't distinguish you, Levke, wearing a scientist hat or wearing I'm a human being hat. But if you could just loosely release the scientist hat for a moment, where do you speculate in the distribution of possible futures? What's your gut feel on where we will eventually land in terms of temperature Celsius above pre-industrial average?
My feeling is we are going to land somewhere where we do not want to be, and that's basically what scares me. I think we're going to land somewhere where we are forced to act, because the consequences are so dire and so extreme. And I mean, the problem is, of course, I think that the regions globally that are more vulnerable are not the ones where the power and the money sits. And that basically means that we are probably going to see the consequences maybe more in having more refugees and having more war zones and stuff like that. And it doesn't matter what the number is going to be. I think the reality is not going to be nice.
I was just in India, in the south of India, and most people there don't know about climate science. They just know that it's 100 degrees there today in the south of India. And it kind of broke my heart, because up until that moment, I cognitively knew that there's 1,400,000,000 people in India, and the Indian subcontinent is one of those places that is going to warm and have higher wet bulb issues. But to be there in person and see the real warm, lovely people and culture, it kind of hit me, because I visualized some of this happening, not centuries from now, but in the coming decades. So I hear what you're saying. How do you, and we'll get back to this, but I want to still ask you some questions about AMOC. How do you and your colleagues measure AMOC? How can you even measure such a thing?
Yeah, very complicated, actually. So even a few years or a few decades back, I think the first AMOC measurement that I know of, like a real measurement, basically where they went into out onto the North Atlantic and put instruments out into the ocean, is from 1959. And back then, what they had to do is basically they really had to go on a research vessel and then drive along the whole width of the Atlantic, because you really have to go from basically Africa to the US and or Brazil, basically, to really cover the whole length, to take into account all of the water masses that are being moved. And that's how it was done for most of the time. And from these first measurements, and that's very costly. It takes a couple of weeks to actually do this. And yeah, just being on a research cruise every single day is, as I said, very expensive and resource extensive. But these first measurements that they made indicated that the AMOC slowed down by quite a bit between 1959 and I think the last measurement was in 2001, where they really assessed that. And the first estimate was a slowdown of 30% over that time. And that was, of course, dire news, but it also led to a lot of scientists saying, well, can we really say that? Because this was deduced from 5 measurements, so 5 research cruises, basically, going out there over a course of 40 years. They were done during different times of the year, so some were in spring, some were in autumn. And basically what they always gave us was one snapshot of AMOC strength in time. And I mean, basically, if I would try to understand how temperatures are changing, and basically I'm measuring the temperature right now, today, and then tomorrow I'm going to measure the one in the morning, and then the next time at night, then I know, even though I have measurements from 3 consecutive days, I can't really deduce any trend from them because they're measured at different times of the day. And we know that there's internal variability with the day cycle. And the same is true for the AMOC, but on time scales so that we are not completely aware of yet. So there's not just an annual cycle, but there's an interannual cycle. And long story short, that's why they started in 2004 to put instruments out into the Atlantic full time, to really have a continuous measurement. It's still very costly. It's a lot of work. So you have to have like research or scientists getting out there, putting the instrument in. They have to be exchanged every 1 or 2 years. They have to be calibrated. But from 2004 on, we have AMOC continuous data. The only thing is basically that 2004 until now, that's 20 years. When we are looking at climate change, we don't talk just about 20 years. We talk about at least 30 years or longer, because we know that there are internal variabilities at place and things can basically happen, or you can have a trend over 2 to 3 years. That's not a long-term trend, but that's just really related. For example, I guess most people know the El Niño phenomena. All these things have effects on the Earth system.
So how does the AMOC relate to, or does it relate to, the Gulf Stream? And is there a risk of the Gulf Stream slowing down?
So the AMOC and the Gulf Stream are 2 interesting brothers, I would say, in the sense of sometimes we even talk or call the AMOC the Gulf Stream system, because they are closely linked, but they are different. And the important difference is the Gulf Stream is in surface current. It's a wind-driven surface current. Basically, we have wind systems over the North Atlantic. They push the water masses. Due to the Coriolis effect, the water masses are deflected to the right. And this basically leads to the Gulf Stream flowing as it does. The Gulf Stream is, when we look at the size of the Gulf Stream, it's way bigger than the AMOC. So depending on where you measure, whether it's close to Florida or more towards the outer North Atlantic, the Gulf Stream has a volume transport between 30 to 150 Sverdrup. And Sverdrup is this unit used by physical oceanographers. 1 Sverdrup is 1 million cubic meters of water that are being transported per second. So Gulf Stream between 30 and 150. Maybe just as a comparison, the Amazon River, the largest river on Earth, has a transport of 0.2 Sverdrup. So what's being transported in the Atlantic is huge. But most of the Gulf Stream waters are then basically also end up on the return way as a surface current. And with return way, I mean basically the Gulf Stream is flowing northward and is then being deflected to the right and to the right due to also to the wind system. And we have a southward surface current along the European and African coast, basically. We still have a little bit of a heat transport because we have the warm water masses going towards the North Atlantic. They're being cooled, and a little bit colder water masses going back. But when we talk about the AMOC, we have an exchange of surface flow going towards the North Atlantic and deep water, really cold flows going southward. So in terms of driver, for example, we could say the Gulf Stream is driven by the winds. The AMOC is mainly driven by density differences. Mainly, I'm saying mainly here because when we go out there and measure the AMOC, we can't ask the water masses, hey, what's your driver? Are you moving because of the winds or because of density differences? We just see moving water masses. And because of that, we would say probably that a small percentage of the Gulf Stream is basically ending up into the deep water formation region and is then becoming part of the AMOC. But the majority of the Gulf Stream is just being also traveling back southward as a surface current. And that part is not slowing down as long as we have the winds. When the AMOC will collapse, then the Gulf Stream would slow down a little bit, that AMOC part of the Gulf Stream.
And warmer temperatures affect both the Gulf Stream and the AMOC, though, because the winds, to my knowledge, are created by the temperature differential between the equator and the poles. And if the poles warm a lot, then that temperature differential declines, and that would reduce some of these winds, yes?
Yes, that is true. I think although when we measure it right now, the wind effect is really not that large right now. But in principle, you are right that's happening. This polar amplification is decreasing the temperature gradient, and with that, the wind strength overall.
So in one of the presentations that you have on your website and that you shared with me, you have a slide which we'll put on screen where you highlight that the AMOC effect has potentially is part of a domino effect in some of the other issues dealing with the Amazon and the West Antarctic ice sheet and the Greenland ice sheet. Could you talk about the feedbacks and the domino effect that relate to not only AMOC but the climate system?
So the AMOC, I think, is special in the climate system as it's the one major connector between southern and northern hemisphere, between the Antarctic ice sheet and the Greenland ice sheet. And when the AMOC, let's assume the AMOC would slow down by a lot, we kind of said, okay, that means more excess heat in the southern hemisphere, less in the northern hemisphere. That could, on the one hand side, stabilize the Greenland ice sheet because it's cooling down the subpolar North Atlantic around Greenland and could therefore stabilize that ice sheet, but it would lead to more heat around Antarctica and could therefore lead to more melting there and destabilize. When we look at Antarctica, mainly the western part is the one that we are worried about the most right now because it seems to be the most destable one already. And with that, of course, then enhanced sea level rise. But, and this is really important, it kind of shows that the order of things happening has an effect. Because if the Greenland, I said a slowdown of the AMOC could stabilize the Greenland ice sheet. If the Greenland ice sheet is tipping, then this would actually lead also to a destabilization of the AMOC. Because if that basically is the order, because we have a lot of fresh water then melted on Greenland and flowing into the subpolar North Atlantic, and I explained already how this can slow down the AMOC. So, but it shows that the whole Earth system is linked, and when we have those major effects happening, more can follow.
You may be too young, and I don't know what TV shows there were in Germany when you were growing up, but do you ever get the feeling that this is all part of some Twilight Zone episode that we're describing this the biogeochemical cycles of the planet that you and I are alive on, and we're talking about major Earth system changes happening on our watch? Doesn't that just blow you away at times, and not in a good way?
Yes, actually, yes. And I think it feels so strange that as humans, I mean, an individual human is very small and in a way, I don't want to insult anybody, but insignificant. And for example, when I go out on the North Atlantic on a research vessel and you're out on the ocean, then there's huge water masses, so much power around you, so much energy. And also when we look, I mean, I talked about the volume transport by the AMOC. That's huge. That's nothing we can do basically in terms of engineering. So I had actually people contacting me saying, can't we put some kind of robots into the water and move the AMOC ourselves? No, we can't, because that's way too much. That it's so huge, the system, that we can't do that physically. And yet we are actually messing with the system by something as burning coal, by putting CO2 into the atmosphere. So by actually doing, affecting even tinier particles. And it feels very wrong, very scary, I guess. Trying to be optimistic. Okay, it shows that we can actually affect the system a lot. But yeah, it feels like we are playing with something and we don't know the rules.
Is there, and we can talk about this, I'm a science communicator, and I know that people that follow this channel are very fluent in these issues, but relative to the general public, the AMOC and ocean risks are relatively unknown, especially in my country. What about in the scientific community? Is there increasing consensus among your colleagues on the AMOC and climate and scenarios going forward, or is there still quite a bit of disagreement on the broader trends?
There's certainly an increased amount of consensus. So when I basically did my PhD and I published my first paper on an AMOC slowdown, there were quite a few scientists who made the point to me that there are other explanations for the signals that we are seeing. And I mean, the difficulty here is, I mentioned the real direct AMOC measurements started in 2004. So to know what happened over the last century, we have to look at what we call proxy data. So other climate variables that we can measure, that we know are related to the AMOC, and then kind of deduce the AMOC evolution from them. And I worked with my PhD supervisor, Stefan Rahmstorff, on looking at the sea surface temperatures in the North Atlantic. And there are a lot of reasons why we know that they're linked to the AMOC, but of course they are also influenced by other things. For example, an increase in wind strength could cool the North Atlantic, as would an AMOC slowdown. And while there was no one in the scientific community who said, you must be wrong because of that, there were a lot of people saying, well, but it could also be a change in the wind system. We don't know that yet. We don't have the data to support that, but you can't be 100% sure. And I mean, that's true. I would say in all of climate scientists, we basically are never 100% sure, because that's not how science works. We make an assumption, we look at the data, and we try to explain all the data that we have according to that assumptions. And if we find something that is basically disproving what we thought first, then we have to find a new assumption. This has changed because there have been more and more publications that indicated an AMOC slowdown and none that showed the opposite. There are still some data where we are, okay, this is interesting. We can't completely complain that yet. But with that, the consensus is definitely increasing. I think one problem is also just the way the science community works as a whole. So it's not that there's one publication about something and everybody's, oh yeah, now we're going to believe that. It's more like, oh, interesting. Now let's wait a little bit, see what other research groups are publishing on that, test that. I mean, that's good. That's how we can make sure that we are not basically following some random group, but that we're really getting to enhance our knowledge. But it also makes us a little bit slow, and maybe with regards to climate change, too slow.
It's so complex, and I'm sure you deal with ocean AMOC experts in your paper writing and your job. But then there's Arctic climate specialists and cloud physicists, and there's all sorts of different disciplines within the climate discipline itself. And how do you all meet at conferences and compare notes on things that you're not experts in that someone else is? What's your experience there?
My experience is that the different disciplines are too siloed, basically, so then don't talk enough to each other. And I think it's not just a problem within the disciplines, but also with the way science is being done at the moment, that it's really pressed towards publications. As a young researcher, I know basically I'm being measured by the amount of first author and second author publications that I have. Because of that, too many papers are being published and no one can read all of that. But to publish a paper, you have to find something new. And I think what we really have to do more is actually synthesizing the data that is out there, the publications that are out there.
Yeah. So tell me about your work. Where do you work? What do you do? And if you and your team are successful, what do you hope to accomplish?
Yeah, here I have to admit that basically I kind of left the AMOC community, the very small AMOC, or not small, but the focused AMOC community, because of the experience I made in the last years. That basically the AMOC is a topic that is able to raise attention, maybe also because of this movie, The Day After Tomorrow, and at least in Europe, a lot of people know about the Gulf Stream and the importance. But there are so many things happening when we look at the increase in extreme weather events, when we look at floodings, and I feel that the increase in fires, so many things related to climate change that happen on way faster timescales than the AMOC, and that have a big effect right now, that I basically went to my former institute, the Potsdam Institute for Climate Impact Research, and now work with Johan Rockström on the planetary boundary framework, which is highlighting actually this global approach and this synthesizing approach, saying it's not enough to just look at one special corner or area. And this is actually going further, saying, okay, not just AMOC is enough, not even just climate change is enough. We really have to look at the Earth system and looking at all its components, looking at the biosphere integrity and basically how the biosphere is right now functioning in our favor, because that is also taking up a lot of carbon, how it's basically working in terms of the radiation budget. And I just feel that we know so much that we can do that would improve the lives of so many people on Earth in terms of course, reducing CO2, but also living more sustainable, changing our diets towards more plant-based, that I just wanted to work on that. And I think the problem is in getting people to act that most want numbers and certainty. And we can't give 100% certainty yet, and we can't give the exact numbers, but we can give with 99.9% certainty the direction that we have to go. And I just want to press that and work on the science there.
This is an interesting thing, because if we stop this conversation now, you have outlined scientifically, credibly, in some detail how the AMOC works, and my viewers will have learned about that. There's a wide variety of viewers that follow this channel because we cover all the aspects of the human predicament. But once we go into what should we do about it, I'm sure you have some suggestions. Then once we talk about prescriptions, then some people no longer believe the scientific description. And I'm not talking about you. I'm just talking about generally in the world. There is the explanation of the issue and there's the what to do about it, and they confound each other. Have you experienced that?
Yes. And I'm not 100% surprised by it, because it often seems to be human nature, right? That we find it really difficult to change. And when we look at our everyday life, I guess most people know basically what would be best for their own health in terms of exercise, diet, and so on. But they seem to be not to be able to do what's best for them in the long term. I guess short term, I can basically say, okay, I want to eat this right now, so I do it because it makes me happy. And so it's not surprising that when it comes to this even bigger and more longer term issue, that of course we are not able to choose what's best for us in the long term, but it's also really, really frustrating.
I think if 10 or 20 or 30% of people chose the better path for climate, there would be a social primate pressure to do that. But since it's someone else's problem and in the future, so far we've not done that. Plus we are individual humans as part of this globally connected, emergent, energy hungry pseudo organism that has a life of its own. So climate is a real problem for this situation, and the only antidote that I can think of is more conversations like this that act as a facilitator between our current behaviors and our mental understanding of the future.
I agree. I think that the best way still to basically facilitate or induce change is to explain things, to understand things, because if it's difficult to change, then we will only change if we really get the reason.
So earlier you said, and I happen to agree with you, that we're going to do business as usual, make a few little benign tweaks on the margins, but not do anything major until we see the temperature, precipitation, ecological impacts are horrifying, and then we're going to try to do something radical at the last minute. Do you have any speculation on what some of those radical interventions might be?
Uh, Oh, I don't know yet, because I guess it's kind of like a path I don't really want to go down in my
Yeah,
mind. I
yeah.
mean, the thing is, of course, that there are, as far as I know, there are not like real international laws on what kind of climate or geoengineering is allowed or not. So I'm afraid that some people might be thinking, oh, cool, now we put a lot of aerosols into the atmosphere because that at least has a cooling effect for a few years. I know that I mean, those ideas have been tested in climate models and basically run through, and none of them seems to be promising for the moment. So I'm afraid that anything radical that we do is probably not going to be wise.
So, could you offer any non-radical suggestions to our viewers, either as individuals or as parts of institutions that create policies? And my view is Germany or the United States can't just be climate friendly policies and go to the Paris Accord agreements. It's a global, the CO2 is not recognized national borders. I mean, it's a global thing. So what sort of recommendations do you have to avert some of the default paths that we're currently on with the AMOC and with the global climate system?
I mean, in principle, it is very simple. First of all, we really have to get our CO2 emissions down. And I think personally that means, on the one hand side, I would really encourage people to basically look at the political party that they support, and this topic should be in there. And I mean, I'm not basically, for me, it's not really important whether otherwise what kind of faction you support and whether you like are a fan of capitalism or free markets or whatever. The climate topic should be in there no matter what the party is, because that's non-negotiable, and that's nothing we can basically we can't talk to the climate system or to the earth system and say, hey, now we're going to pay you this amount of money and you're not going to change. So that's important, and please stress that no matter what you otherwise basically stand for, believe in. And then the other thing is also be skeptical, I think, because we like easy solutions, but normally the easy solutions is not the best solution. And I think that's just something most of us know, right? If we work hard for something, normally it stays longer, basically. What I gain in a minute, I can often lose very soon also. What I gain with hard work over years, that stays. And I think, so with that, be okay with that. It's going to be hard, but it's not going to be negative. A lot of the decisions or changes that we have to make, as I already mentioned, would also be good for ourselves. I mean, we do know that a plant-based diet is better for most of our health, and that basically cycling a lot. I mean, who wants to sit in a car all day and drive around? Maybe a few people do, and that's okay too. I think kind of try to find the changes that are okay with you. Nobody has to change their life completely, but we can all make changes that basically make our lives more sustainable. And I think that's also important to like really take care of that and do the effort, and don't do it for somebody else, but basically do it because it's the right thing to do. That makes sense.
It does make sense, but as I said, climate is a global issue, and we've got India planning to double coal production in their country by the year 2030. And you can understand why they want to do that, because they're going to have higher temperatures and they need more air conditioning and cooling for their population. So there is individual recommendations, and I agree with the ones that you laid out, but there's got to be some sort of global plan, and there isn't, and I know why there isn't. So is there any hope in the international scope of things that you and your colleagues have? I think these COP meetings so far have been a real disappointment. They have no teeth. And I think the difficult questions are not askable with all these high status men and women from around the world, because they don't like truth to power sort of questions.
Yeah, that's a very good question. And I have to say, basically, there's a reason why I'm not in policy, because I like honesty and I like being direct, and I can't deal with people who try to tell me something by, I don't know, going around the issue and telling me something else. And with that, I'm also very frustrated. And I think, honestly, that this lying on lying on that level, on an international level, and with lying, I'm also meaning that if you draw attention away from the truth, or you hide some facts, that should be really punishable, I think, because it is misleading and it's hurting so many people. I'm also hopeful because I've actually met a few people that are active in policy and that have great ideas and that are really, really enthusiastic and engaged and try to protect others, those who can't protect themselves. But of course, I do see that we are not really getting closer to a solution right now. And I honestly don't know how to change that, how to help that. I think if there are people out there who know that their strength is to influence other people, basically, and to get them to basically do what you want them to do, then please use it for good. That's what I'm asking you. I can only give you the facts, but we see that delivering the facts is not enough, right? That's what we've seen, that's not enough. We kind of probably need some kind of climate lobby where we really say, hey, people, this is what you have to do.
Maybe we need effectivists instead of activists. So let me ask you a personal question. You're obviously very knowledgeable and passionate about this topic, as you should be, because this is the topic of our times. Well, one of the core ones anyways. How do you manage being all in, as you clearly are, on ocean issues, planetary boundaries, where we're headed, and then have a normal life and have cheeseburger or strudel or whatever you eat there with your high school friends and your family? How do you live in both worlds? Because I struggle, to be honest, in my life with that.
Yeah, I do too, and I guess I'm not completely sure whether I'm leading a normal life compared to everyone else. I would say that when I look amongst my friends, most of them basically support the same things I support. So I'm really living in a little bit of a bubble, and most of them really try to be as sustainable as possible. I think it would be difficult otherwise. It's something that I do see with family, you don't choose your family, right? You are born into it. And there I'm having sometimes complicated discussions, and sometimes I just decide not to discuss certain things. And in other terms, I have to say that this kind of is also affecting basically how I plan my life. And I do see that basically, I would say the goals and dreams that my parents have given me, and kind of saying, hey, I'm 34 right now, so I should probably have 2 kids, a husband, and a house. And basically, I have a partner, fiance, I'm very happy with, but we never plan on getting a house because that's not really, I think, realistic. achievable for most people. So I guess that, of course, but some people can have their own house and their own place. But when we look at the number of people we have on the planet, our limited resources, then not everyone can have a house. Actually, most people can't have their own house. And it's also really when we think about, okay, do we want or not have children? Do I want to put my children into this kind of world? Will I be able to adequately protect them with what's coming in the future? These are things I'm discussing with my partner and with my friends, because it's not just about what is my own happiness basically, and do I give on my genes to the next generation. We certainly know that in terms of population, we don't need every one of us to get a child, so we are enough people on the planet. And of course, in terms of resources, not having a child is way smarter than having one, which is not saying that nobody should have children, of course, but it's something that I think is in there. I know of those things. I know of the limited resources, and I can't forget it when I basically enter my private life, what I learn or do during my work time. So I struggle as you.
Long ago, I chose not to have children, genetic children. You and I both have cultural children in a way with the young people that we influence with these ideas. And I have ducks and dogs, which also eat resources, but that's the path I chose. So let me ask you one more scientific question, and then I'll get to the closing questions that I ask all my guests. Would it be fair for me to say that this year will be the coolest year of the rest of my life on average? Of course, there could be El Nino and La Nina and other things, but is that a fair assessment to make given what we know about the inertia of the climate system?
Sort of. I mean, you just chose basically an El Nino year, which of course we know is
true.
A global average, a higher temperature. So I very much hope that the next 2, 3, 4 years will be on average a little bit cooler again.
Yeah.
But in terms, of course, of the long-term trends, yes. So basically, I wouldn't see like a large-scale cooling signal is not going to happen within the next decades, even if we would stop all emissions right now. So
Yeah, thank you. That's my understanding as well, but I wanted to back it up with a climate scientist. And I will have Johan, your colleague, on in the near future. He was supposed to be on tomorrow, but we had to reschedule it. So, Levke, I really like you, and I respect what you're doing, and I feel the passion and frustration bubbling just under the surface, because this isn't our fault what's happening, but you and I were born on this planet as humans during this time of the carbon pulse, and looking around us and figuring it out is someone's job, and I'm glad that you're doing it. So do you have any personal advice? You just mentioned about houses and children, but do you have any personal advice for the listeners of this show that are hearing what you're saying and concerned about the future? What sort of advice do you have for the listeners?
I would say on the one hand side, kind of be creative in your dreams. I kind of mentioned that we don't have to have the same goals in terms of having or becoming rich, having our own house, or having to basically fly, have a vacation somewhere fancy, tropical every year, because that's not necessarily what makes you happy. So really like listen in your inner self, basically, what really does make you happy, because I think most of the stuff that makes you happy can be very sustainable and totally fine and be done within the Earth's resources. But then the other thing is, I still believe and try to act under the assumption that humans are good and that nobody really wants to be a bad person or tries to harm others. I mean, there might be a few exceptions, but I think most people, even if they actually do something right now that is causing a lot of emissions and harm to the environment, they have a reason that can probably be understood by us, because there is a reason in their reasoning why they're doing this and why it's a good thing to do. And so it would be good. Of course, we have to educate those people and we have to try to change them, but we shouldn't make them to monsters, and we should act in the way saying, hey, okay, I see what you're doing. This is how it's like. Why I don't like what you're doing, because it's hurting this and this person. Can you explain to me why we're doing it, and maybe we can find a solution together. So I think that's important to also just stay optimistic and to like life. And also because I really believe it's true. So most people I talk to, when they do something where like, how can you do that? Then they explain it to me and like, oh, okay, yeah, now it makes sense. But hey, there's actually a different way of how you can do this or this, which is way better for the environment and for everyone.
And how would you change that advice for the young people watching this show in their teens or 20s who are becoming aware of all this and they have a whole lifetime ahead of them?
That's a very good question. And I would say, I'm not completely sure what I would say. I would probably apologize for not having taken better care of their world so far. I mean, and I'm still fairly young. I would say be bold, basically. Just because you're young and it feels like you might know less, and that's something I experience as a scientist. So I mean, I'm talking to colleagues who have 20 or more years experience than I have in the topic. And sometimes still I see that they make mistakes, and it just takes me more longer to be brave about that and say, hey, no, I'm studying this too, and you might have more experience, but I put a lot of time in this, and I know I'm right. And I think that's also with the young people is when you feel something is not right, be brave about it, be bold about it, and change. Otherwise, probably also be hopeful, find your own future. But in general, I have to say it's hard for me. It's hard for me to be like completely optimistic towards a person who has, 70, 80 years ahead of them, because I know that life is going to change quite a bit during that time.
So this is a question I ask all my guests, and I think you may have subliminally, through your things that you've left unsaid, have given the answer. But what do you care most about in the world, Levke?
It's probably a fair and honest world. So I think that this is what bugs me most about, I guess, this topic, is that the main people who are causing the problems are not the ones that are suffering the most. And that's just not what I like. So it's really this fairness. And
the main non-humans are going to suffer as well.
That's a very good point, yes.
Yeah. So if you could wave a magic wand, what is one thing you might do to change human and planetary futures if there was no personal risk to yourself?
Kind of depends on the limit. I mean, if I could basically change the climate system, the Earth system, back to a pre-industrial state, and fix it in that way that no matter what we do, we couldn't change it as humans, that would, of course, be a safe way, although maybe we wouldn't then learn. I think if it comes to the human mind, as I said, I would really like us to be able to make the wisest decision, to be objective, look at the facts, and then decide what we do based on them and what we want to happen, and not based on this weird mix of emotion, fear, maybe favors. Yeah. So that, I think, would already bring us a very big step further towards a sustainable future.
Thank you. If I were to have you back on the show, which I would love to, what is one topic in your broader work that isn't a broad overview, but is a very specific topic that you think is relevant to our future that you would be willing to talk about in depth?
The next time, well, given my location, or my job right now, it would really be about the link of the climate system towards the rest of the Earth system, towards with the land system, with species diversity, and how all of this is basically connected, but from a scientific point of view. So not from a spherical point of view, Mother Earth, but really we see so much scientific evidence for that, and I would love to talk about that.
Excellent. Any closing words for our viewers and listeners, Levke?
I guess, honestly, if they listened until this point, then I would thank them for being so interested in the science. because, I know it's a complicated topic, and I know that it's hard to understand. And I mean, I've been doing this for 10 years nearly, and I'm still learning new stuff. So, thank you for your openness to learn about these things, for your willingness, hopefully, to change. That means a lot, and that's, I think, what the world needs.
Thank you so much for your time today, Levke, and for your important work on this issue. To be continued, my friend.
Thank you, Nate.
If you enjoyed or learned from this episode of The Great Simplification, please follow us on your favorite podcast platform and visit thegreatsimplification.com for more information on future releases. This show is hosted by Nate Hagens, edited by No Troublemakers Media, and curated by Leslie Batlutz and Lizzie Siriani.